tonight's program. They fund all of the programs that we offer for kids, teens, and adults. And one other thing that they have generously funded, if you've been to our programs recently, you might notice that you're sitting in brand new chairs. You're the first people to be sitting in these chairs.
Thank you.
Friends generously helped us with. So I just wanted to mention that. Thank you all for being here. We are so excited to have Nico Carver here to give us sort of an intro to astrophotography. It's really exciting to have you here, and we're excited to learn more. So I'll just turn things over to you.
Thanks, Nicole. Thanks everyone for coming. So, has anyone done astrophotography before, just by a show of hands? Just okay. Yeah, great. And what kinds of astrophotography have people done?
Took some pictures of Halley's Comet a long time
Halley's
ago.
Comet? Great.
Yeah, that was fun.
Time lapse, okay. Anyone else? Yeah. Okay. So there's a lot of different kinds of astrophotography. You can think of just like, you've probably seen pictures of our Milky Way, our own galaxy. And so those are wide field kinds of astrophotography. There's pictures of things in our solar system, like so we get occasional comets that come by. Of course, there's other things in our solar system that are really bright, like the moon and the sun. You can also take pictures of those. The kind of astrophotography I'm the most interested in is called deep sky astrophotography. And that means objects that are outside of our solar system. When we're talking about nebulae scenes like this one behind me, that's in our Milky Way galaxy. So there's all this dust and gas in our Milky Way galaxy. It's how stars form. And we can take pictures of it with just normal photography gear. This kind of picture right here was just taken with this setup. And I think that often blows people's minds because they think that you see a picture like that and they think, oh, you must have a massive telescope to do that, right? But no, you can do a lot of this with just regular kind of telephoto lens and a DSLR. So that's what I'm going to talk a little bit about tonight. But before I get into that, I'll just sort of introduce how I got into this hobby. It started for me on a trip to Iceland over 10 years ago now. And I went to Iceland in December, which a lot of people don't do because it's very cold, and most days it was like, you know, sort of horizontal precipitation, like ice just sort of blowing in your face. So it wasn't really that nice to be like outside. But I went specifically to see the Aurora Borealis because I'd seen them briefly before in Alaska, and then I sort of got into the idea of like, I want to see them in a really cool place, so I picked Iceland, and I got very lucky. The very first night we were there, we were just driving around, and I looked out sort of my driver's side window and could see something on the horizon. I got out of the car, and I could all of a sudden, once my eyes adapted, I could see they were filling the entire night sky. So from horizon to horizon, we were seeing these beautiful green lights. When the camera picks them up like this, they are a little bit more vibrant than the eye can pick up at night. And then the other thing to note here is this is time-lapse photography, which is what I was really into capturing at the time. So this is also sped up. This isn't real-time video. There are cameras today, especially these Sony cameras, that you'll see actual real-time video of the aurora. And usually it's a little bit slower than this though. Here's another one, and this was a few nights later, and what I really enjoyed about this, maybe you could just barely see it on the side here, these people setting up along the lagoon, is that it became this kind of star party. It became this place where a bunch of photographers from all over the world gathered because this spot was well known, because it was often still, so you get the reflection of the aurora and the stars in that glacier lagoon. So it was really cool to meet all of these other people, and this is really what sparked my interest in astrophotography, because when I brought this home and saw these stars, I got really interested in this, because I'd never really done night photography before. And what I was really into at that time was filmmaking and time-lapse, so I actually just made this as a time-lapse, and then months later I thought, well, what if I just took a single photo out of that time-lapse and brightened it up? And that's when I saw, wow, there's so much in every photo that we take of the night sky that's just really, really dim. right? And if you take it onto the computer and you just take the brightness slider and you move it to the right, all of a sudden you see all these other colors and things come out. So this is just a single 15-second picture with a wide-angle lens, and all I did to it was take the brightness slider in Photoshop and bring it up a little bit, and that's what came out. So some astrophotos can be really brilliant, and they're just a single picture. If you get really lucky like I did here, maybe your first astrophoto could be something really, really cool. Did anyone capture the aurora when it was visible here in Massachusetts? Yes. And what I loved about that was we could now capture it on just smartphones, right? They've gotten so good, and what they have now is they have, I'll talk about stacking a little bit later in the presentation, but they actually take multiple pictures and stack them together. So you get this long exposure, and they call it night mode, and it really allows you to bring out a lot more detail. So I got home, I was looking through all of these pictures of the aurora. I was getting really into it, but at that time I still thought of astrophotography as something you only did when you have really beautiful locations, when you're under a really, really dark sky. So I had a work trip out to Las Vegas, and I was sort of looking around there, and I was like, oh, Death Valley isn't too far. So I extended the trip a little bit and went up to Death Valley National Park, and this is called the Playa. It's this salt basin, and these stones, I don't know if you can see this, but they make these sort of tracks on the Playa, and they call them the sailing stones. And for a long time they didn't know why these giant boulders created these tracks, because there was no real reason they would. But then what they did is they set up these video cameras, and they realized that the Playa occasionally in spring will get a very thin layer of ice over the entire thing, and these giant stones will actually just sail along the ice with a slight breeze because the Playa is so flat. And then what's left over are these tracks in the dirt. So I thought that was really a cool story, and I wanted to sort of emphasize them, so I took the tracks and have them lead your eye into the core of the Milky Way there. This was again just taken with a setup like this, but instead of a telephoto lens, it'd be a wide-angle lens, a 14mm wide-angle lens.
Question?
Yeah.
Is that also more vibrant than it was here?
Yes. Yeah, this was also processed, and yeah, that's a good question. So the question was, is this more vibrant than it was to the naked eye? Yes, but I will say that this was one of the darkest skies I've ever seen in Death Valley, and what you could see, naked eye, was see how down the center of the Milky Way there's all of that dark part? You could make that out very, very well. So normally under a fairly dark sky here on the East Coast, you can sort of see there's a dark band in the Milky Way. But under a very dark sky like in Death Valley, it's detailed. Just with your naked eye, you can see all these different shapes in it. Where that little, where all those little bands of dark come out, you can even see those. Is the Lagoon Nebula in this? I wish I had a pointer, but you can actually see some of the bright nebula and star clusters naked eye too. Okay, so I think I've already sort of emphasized this, but the gear, what I'd really suggest doing is if you're interested in astrophotography and you have any kind of photography gear, just use what you have to get started. I wouldn't suggest going out and buying something right away, because what I find is when I advise a lot of beginners in this is they go out and buy a bunch of gear and they think that that's going to make the hobby easier. But actually, if you use what you already have, that's going to make it easier because you already know your own photography gear. So what I would suggest is use what you already have. The important thing is just getting to a dark site and trying it and just practicing it. So what I would say is a nice just sort of beginner setup, what I brought here, is a tripod with a tripod head. And really any kind of tripod will work, but you just want to make sure with the tripod head that you can actually point your camera up at the night sky, right? Because some tripods, especially if they're designed more for filming yourself, maybe they only go up so far, right? Well, you really want to be able to shoot something up there, you want to make sure that your tripod head can do that. So this is called a ball head, And most ball heads have this little notch right here that allows you to point the camera up like that. So that's the one thing to look out for with the tripod head. If you're looking for a tripod, because you don't have one, what I always tell people is don't buy the cheap one on Amazon. It's going to be mostly made out of plastic. Go to eBay and get a used one and look for the brands Manfrotto. It's M-A-N-F-R-O-T-T-O, or Bogen, B-O-G-E-N. These are Italian brands, and they make aluminum tripods that you can buy for $60, $70 that are going to be much, much better than the sort of modern plastic tripods. Okay, and then I said wide angle lens here, but it could be a telephoto lens too. Any kind of camera, it's probably better if it's one that has, it's called an interchangeable lens style camera. So this is a DSLR or a mirrorless camera. And the reason for that is these kinds of cameras, you can often get faster lenses. And I'll get into what that means in a minute here. But basically it just means that you can take the camera body off and put on a different lens. And that gives you a little bit more flexibility. You can change from wide angle, if you want to do Milky Way, to telephoto, more zoomed in, if you want to do deep sky. Okay, and then just a couple little accessories help. The first is called a shutter release, and I'll explain why this is nice. So, if you are taking a picture of the stars, and you have it all lined up like this, and then you press this shutter, even if you don't feel like this is shaking it, it's probably shaking it a little bit. And then what you'll see in your picture is the stars won't be sharp. They'll be blurry because you just shook the camera by touching it. So if you have this wired release, when you press it, no shake, right? Because the camera on the tripod stays perfectly stable. Then the other thing you can do with this is you can click and lock it. Did you hear that? The camera is taking one picture after another. And that is really helpful because we'll get into this, but there's something called stacking in astrophotography. So we actually take multiple pictures at once. Do I have it on here? Oh, not picture. Okay, another thing that's nice to have is called a dew heater band or a lens heater band. And this you can usually power off like a little USB battery. What it does is, especially around here in Massachusetts, New England, you're going to find that on many nights, if you just have your camera set up like this outside, what will eventually happen is this front lens element will get dewed over. It will pick up condensation from the air. And the reason for that is because the glass is slightly colder than the air temperature. So if you warm up the glass slightly warmer than the air temperature, you won't get any condensation on it. So this is a nice thing to have. I don't have it pictured here. If you don't want to go out and buy a dew heater, or you forget about that, but you do have one of those chemical hand warmers, you can actually just rubber band a chemical hand warmer to the lens, and that works just as well. You can pick them up at gas stations for about $1. Okay, and that's all the gear that I'm going to be talking about tonight. Are there any questions so far? Okay. But I'll go a little bit deeper into like how to use this gear here now. Okay, the first thing is with the camera. A lot of people, want to know the camera settings to use. And this is a big one. If you want to get the most out of your pictures, if you're planning to bring them onto the computer and process them on the computer, which is the common thing to do with astrophotography, you want to shoot in RAW format. And the reason is RAW format captures a lot more data in the picture. It's going to be a slightly bigger file, but it allows you to bring up those shadows. And a lot of the detail in astrophotography is in those shadows. And so shooting with a RAW format is important. The typical option is called JPEG, and that's a compressed format where it already has compressed the picture on the camera. Okay, and then the other settings is really just making all the exposure and focus settings manual. So on most cameras, you'll see M for manual. So you'll change your dial to M. On the lens, if you have this switch, automatic focus or manual focus, change it to manual focus. Okay, and then we'll get into the exposure settings. So once you've changed your camera to manual, what that means is, normally if you have an automatic mode, right, you put the shutter down halfway, it has a little exposure meter inside, and it looks at the scene, or it looks at part of the scene, and it adjusts those settings for you to get the right exposure. It knows how to do that for daytime indoor shooting. It does not know how to do that for astrophotography, for shooting the night sky. It looks at the night sky and it's just like, this is perfectly black. I don't know what to do. It just gets confused. So that's why we have to put it on manual and change those settings ourselves. The first setting to change is called the shutter speed. And so this is how long the camera sensor is open to the night sky. And this is a sort of confusing chart, but I'll explain it. When we're taking a picture of the night sky, we can only expose for so long before the stars are trailed, before they turn from points to lines. And so the old rule of thumb was called the rule of 500. And the cool thing about it was easy to remember, because all you had to do was divide 500 by your focal length, and that gave you the shutter speed in seconds, right? So 500 divided by 50, it gave you 10 seconds for the shutter speed. For single shot Milky Way, like if you're doing a 14 millimeter big wide shot, the rule of 500 is going to work fine. But for stacked astrophotography, for this deep sky, we want to use a different rule. So what I suggest in my videos is this strict one, this far right column, because I find that it works the best if you're going to plan to bring all your pictures onto the computer and stack them together. So we'll get into what all that means, but I just wanted to show this in terms of settings. And then the next exposure setting is the ISO. And so this is, it takes a picture, it then applies what's called gain to that picture. So it basically multiplies the values that you've captured. And there's some confusing stuff here, but like basically there's a sweet spot for any digital camera where the gain works best for astrophotography. And it's usually between 800 and 6400. So this is a little bit different if you're coming from the normal photography world, where you're often told use low ISO, right? Use ISO 100, 200. For astrophotography, because we're shooting the night sky, which is so dark, we want to use a higher ISO. So usually 800 to 6400 is the best sort of spot. And the ISO that I use the most often with a setup like this, where it's just a DSLR on a tripod, is 3200. Okay, last exposure setting is aperture. And so with a telescope, it has a fixed aperture, meaning that you just get one. With a lens, it allows you to stop down the aperture with what's called an internal iris. So this is some pictures of what that internal iris is doing. And as you can see, when you stop it down, you're letting in less light. That opening, the aperture, gets smaller and smaller as you stop down the lens. But there's some trade-offs. While you're getting less light, it usually makes the pictures sharper. So it makes the stars a little bit sharper, it'll make all the details sharper. If we had what's called a star tracker, so we could put this and it could counteract the Earth's rotation, I might stop down the lens to get slightly sharper stars. But for this kind of astrophotography, just keeping it simple, what I suggest everyone do is just make their lens opening as big as possible. So that's going to be the smallest f number, right? So if your lens opens up to f2, make it all the way f2. If it opens up to f1.4, that's great for astrophotography. That means you're getting a lot of light, and so open it all the way up. Okay, and then where all of this comes together is in something called a histogram. So a histogram is just a graph showing all of the brightness values of all the pixels in the picture that you just took. So if you think of all the different pixels, and if every single pixel was completely black, that chart would be, that mountain right there would be pushed all the way up to the left-hand side. If you were completely overexposed and every pixel was perfectly white, it would be pushed all the way to the right side. And in general photography, sometimes you'll hear the term exposed to the right, meaning put that histogram a little bit past 50%. In astrophotography, we do the opposite. We want that histogram peak to be exposed to the left. But where to the left? Really, anywhere in there. Like 1/3 over, 1/4 over, any of that is fine. It basically we just want to see that histogram peak, and we don't want it overexposed by going past halfway. What happens if you go past halfway? It just means that your stars will start turning pure white, so they won't retain any color information, and then eventually they'll start to bloat. So your stars will get bigger and bigger and sort of take over the picture. The other thing you'll notice is that here we have some light pollution, and so light pollution will also become worse and worse, and you'll see that it sort of washes away the picture if you overexpose. Okay, so speaking of light pollution, location and light pollution are very important to astrophotography. If you shoot the same scene, the same part of the night sky from the city in Boston, and then you just travel 2 hours out, it's night and day. You're going to see a completely different picture. And astrophotographers, astronomers often use this scale. It's called the Bortle scale. It was described by an amateur astronomer named John Bortle in Sky and Telescope magazine, which is sort of our favorite magazine as amateur astronomers. I think he described it maybe in the 80s. But anyways, it goes from a Bortle 1 sky, which is like the darkest skies on Earth, like Death Valley National Park would be a Bortle 1. A lot of national parks, like if you really just escape any city, or you're miles and miles out there, that's going to be a Bortle 1. It's mostly important for visual. It's just really impressive visually. Anything darker than a Bortle 4 is going to be great for photography. You don't have to go down to these Bortle 1, 2 for photography. If you can get to a Bortle 4, you're good for photography. Now, can you still get nice astrophotos from these brighter Bortle zones? Yes, but I don't recommend it with this kind of setup. We want to go a little bit more advanced if we want to do astrophotography from brighter light pollution. But if you find, like, right near me it's a Bortle 5, go ahead and try it with this. I'm just saying generally the brighter we get, the more sort of advanced it gets. If you want to get really good photos with a simple setup, you're aiming for this area or darker. And how do you know this information? There's a website called lightpollutionmap.info. You go to this, it has the entire world mapped with light pollution. It does that through satellite data. And that satellite data isn't usually super up to date, but it's close enough that it will give you a really good idea of what areas are more light polluted or less light polluted. And you can zoom in on this map, and then you can click on the map, and it will give you that Bortle scale number. So again, we're looking for something like Bortle 4 to 5 or darker for this kind of photography. Okay, and then this should just give you an idea of the difference here. So I put last night, because this was a presentation I used Cherry Springs. This is a city sky. This was taken with a fisheye lens, and you can see along the lens barrel there's all this glare from street lights. You can also see that there's maybe only about a dozen stars visible in the night sky. Here's a dark location. This is in Cherry Springs, which is in Pennsylvania. It's a good dark sky spot. But you can see that there's just thousands of stars there. It's amazing to see. You can clearly see the Milky Way band going through it. And then you can even see something called air glow. The reason the picture is sort of green is that there's this very faint glow in the night sky at certain times called air glow. Okay, So, all of that stuff, the sort of the getting the gear ready, looking for your good location, that can all be done at home, even inside. You can get everything set up. You can go to the light pollution map. You can decide where you're going to go. Of course, you're going to have to also look at some weather apps and decide, is it going to be clear? Once you get out into the field, the thing that people struggle with the most is focus, because it's very different than normally how we focus. Normally with a camera, we can just sort of look at something, press the shutter down halfway, it autofocuses, and then press the shutter down the whole way, and you're good. With astrophotography, again, because a camera isn't designed to really focus on the stars, autofocus usually fails. With some new mirrorless cameras, it's sometimes working, but it's still pretty hit or miss. So the way that we typically focus is manually. So you start with some bright stars. So what I'm looking at here is the Pleiades. And then what you want to do is go to live view on your camera and find a little magnifying button. So that will do a digital zoom in on live view. And that way you can actually look at those bright stars, and then you're going to change the focus manually with this focus ring on the lens barrel. And what your goal is to make those stars as small as possible on screen. So they're going to, when you first see them, they're going to maybe be nice and big, and then you're just going to move around in sort of the area of infinity focus and try to make them as small as possible. And when you are out of focus, what you'll find is that they're bloated. You'll still see some bright stars. They will look round, and this is a lot of times what fools people, because they see those bright stars, they see that they're round, and they're like, oh good, I'm in focus. But you're not in focus yet there on the left. And the dead giveaway is that if you look at the center of the star, it's dark, right? It looks sort of like a donut. There's a bright ring around a dark center. That's not in focus yet. When you actually reach focus, the bright stars will just be bright like this. And it'll be this really satisfying moment. You'll find focus, and all of a sudden, all these tiny little stars will snap into view. You won't see them at all. When you find focus, all of a sudden, you'll see all these little stars pop in. Okay, so that was the basics. Once you found focus, how do you take a picture like this? So this is the Andromeda Galaxy. It's our closest neighbor galaxy. It's also called Messier 31. It's very well studied by astronomers. It's a very important galaxy. A lot of discoveries of what we know about space have been made through observing the Andromeda Galaxy. And again, I made it with this kit right here. And actually, we're actually seeing 3 galaxies here. There's 2 satellite galaxies, M110 and M32. They sort of are, they're not as detailed though, of course, they're smaller. So, when you go out and you find the Andromeda Galaxy, which you can use a smartphone app to do that. If you're familiar, there's planetarium apps on your smartphone. You can hold them up to the night sky, just move your phone around, and it will actually show you right where M31, the Andromeda Galaxy, is, and then you want to point your camera at it. Once you find it, though, and you take your first 1-second picture, this is what it's going to look like. So, not super satisfying. You can see that hopefully you can see there's a bunch of stars in that picture, right? Yeah. Does anyone see where the Andromeda Galaxy is?
It's on the top middle.
Top middle? Okay, yes. Yeah. So some people see it. And what gives it away that's the Andromeda Galaxy? Fuzzy, right? Yep, fuzzy, and it looks a little different than all those other dots of light. And that's because we're seeing the core of the galaxy, and the core isn't just a spot of light, it's actually this sort of bright ovular thing. So this is all that you're going to see after you find Andromeda and take a 1-second picture of it. So just keep that in mind. It's a hard hobby. You might not be able to get a satisfying picture your first time out. It might take a couple nights to build up to the skills that you need to actually get something good going. But I wanted to sort of just point that out, that this is what you'll actually see on the DSLR, not like the bright galaxy across the frame. And the reason that, okay, so then you might think, well, if I wanted to make it brighter, why can't I just make the shutter speed a lot longer, right? I know that if I let more light into my camera, the picture is going to get brighter. So instead of a 1 second picture, why don't I raise that up to 30 seconds? Okay, and the reason that doesn't work, the only reason that doesn't work, is because we're on a rotating, spinning planet, right? So if you watch the night sky, you'll see if you look at something here, in an hour it's going to be over here, right? So the stars, from our vantage point, are constantly moving, but we're actually the ones moving, right? Because we're constantly rotating around our axis. This becomes very evident if you take what's called a very long exposure star trails kind of picture. You'll see, and this is pointed at the North Celestial Pole, Polaris. You'll see that all the stars rotate around that point. And so we do actually have devices that can counteract this rotation, right? So we're rotating at thousands of miles an hour. You can actually just use a pretty simple device that slowly moves your camera in the opposite direction. And that's all that has to happen to get long exposures of the night sky. So this one is called a star tracker. And that's the one I recommend to beginners who want to start getting into that, because what that does is you just have your tripod, you put the star tracker here, and then the rest of this on top of that. And so it's an easy way for a photographer to get going with this, because it's just one thing that you add to this setup. This is called a German equatorial mount, and it's usually what you would use if you want to attach your camera to a telescope. And the reason it has to be much bigger is because the telescope is much bigger, right? So if you tried to put a big telescope on this, any little gust of wind, it would shake it and it wouldn't work, right? So the heavier your equipment, the heavier your tripod and your tracking mount have to be. And so if you have one of those tracking mounts, this is what the view is from the camera's point of view. You can now see that the stars are staying still there, but you can now see that the Earth is what's rotating around, right? Because it's canceling that out, so now the stars are staying in place. So even though I think these are really cool, I have a bunch of them. When I'm teaching beginners astrophotography, I usually don't want them to take these out on the first 2, 3, 4 nights, because there's so much to learn that if you try to add this too, it becomes overwhelming, I think, for most beginners. Even if you're an experienced photographer, I would say that if you've never focused on the stars, I would go try that first, get that under your hat, and then add one of these. There's also a cost associated with these, of course. Something like a star tracker is usually around $500. This kind of thing, you're getting into the thousands of dollars. So I have a bunch of videos. This is a thumbnail from one about shooting the Andromeda Galaxy. So to get to this picture, we start with this picture, right? This is the 1 second picture. But instead of just taking one 1 second picture, you're going to put your camera on continuous shooting, lock your little control here so that it takes one picture after another. You'll find after you take about 30 or 40 that the Earth has moved enough that Andromeda is now in a different place. So about every 30 or 40 pictures, what you have to do is loosen up one of these knobs and slightly move your camera so that you recenter Andromeda. You tighten that back up, start taking more. And Yes, this will wear out your shutter because the goal here is actually to take hundreds. If you're only having 1 second pictures, we really want to take a lot of them to build up the total exposure time, because this is something very, very dim. Just to show you how dim it is, if we take this 1 second picture and raise it up 5 stops, 5 exposure stops in Photoshop, this is what we get. So the reason we get that is because the camera sensor is so starved for light that we're mostly seeing the noise from the electronics of the camera when we really raise that exposure level. Now, there are some things to reduce this noise. One of them is called calibration. So this is just a single uncalibrated 1 second photo. But if we take what are called calibration frames, you can see we can get rid of a lot of that noise. Not all of it, there's still a lot of hot pixels and things in there, but it looks a lot better after calibration. And calibration frames are not hard. A lot of people are scared of them at first because they're just something unfamiliar. But an example of a calibration frame is just you cover your camera lens. So you just put the lens cap back on and take a 1 second picture with no light getting to the sensor. That's called a dark frame. And when you subtract that dark frame from your picture of the night sky, it removes a lot of the electronic noise on the camera. Okay, so after you've taken hundreds of these 1 second photos, you've calibrated them, then there are free stacking programs to take all those hundreds of pictures and reduce them down into one final picture. So these are the free stacking programs that I recommend. If you're on Windows, Deep Sky Stacker, a lot of people find that the easiest one to get started with. If you are on Mac, you can't use Deep Sky Stacker, but there's another one called Cyril. It's a little bit more techy, but I do have good videos about using it. And then if instead of trying to make a deep sky picture, a picture of a galaxy or a nebula, you're trying to do star trails, this is a good stacking program. It's called Star Stacks. It's free. Once you've stacked all your pictures, you're probably going to want to change the brightness of the picture and the saturation and things like that. A typical program to use is Adobe Photoshop, but if you don't want to pay for that, a good alternative is the GNU Image Manipulation Program. Okay, and then just to show you some of the processing that I would do on Andromeda, here's a sped up version. The whole non-sped up version is on my YouTube channel. And this looks like a lot of different stuff that I'm doing, but I would say that most of it is just using curves, saturation adjustments. It's not anything super advanced, it's just a lot of little steps.
So, question,
Yeah.
so how many stacked images did it take to make that final product?
I believe this one might have been 1,000 1 second pictures, but that's partly because I wanted it to look nice and colorful for YouTube. If you want to just sort of get a picture of the galaxy, you could probably do 200 and still see something pretty cool, like see the dust lanes and everything. The deeper you go with it, the more it's going to be easy to bring up the color, like that blue color and things like that. But the other big thing you can do to get better color is go to a darker sky. So there's sort of two things. Go to a darker sky, take more pictures. Yeah.
And then my other question is, what about sensor size? How many megapixels do you get sensor?
Oh yeah, good question. You don't need a full frame for this kind of thing. If you have a crop sensor, that's going to work fine. Even if you have micro four thirds, it really this is cropped down from a crop sensor camera at 200 millimeters, so way cropped down. So with this kind of technique, really any sensor size will work. You also don't need the newest camera for this. If you do have a newer camera, it'll probably have lower noise, and that will be an advantage. But if you have an older camera, they work just as well. When I'm doing this for YouTube, I always just use Canon entry-level DSLRs, like the cheapest DSLR, because I feel like it's like a good base level expectation for what you can get.
What about mobile phones?
Mobile phones. So mostly they're good for Milky Way shooting because the camera lenses are wide. And then what I found is on most mobile phones, the sensor they put behind the 3x zoom lens is not as good as the main sensor. So I mostly use them for wide shots, Milky Way and stuff like that. You can do stacking still with mobile phones, and some mobile phones now do shoot RAW too, so you can turn that on and there's an advantage there. I've tried doing the calibration frames with mobile phones and haven't had any luck, so I just skip the calibration frames. Oh, the other thing I really like doing on mobile phones is star trails. They're really good for that. So if you want to get, like that shot that I showed of the circular star trails,
Yeah.
there's actually even apps on mobile phones that let you just sort of say start and it creates the star trails image right on your phone. Okay, I already mentioned I have this YouTube channel. So this one right here is sort of what I've been showing in this presentation, but it's an hour-long video if you want to, and most people say, you know, you have to watch it a couple times, but it goes through all the different steps, including the processing steps. So it's called Andromeda Galaxy with only a camera, lens, and tripod. I also have ones with this kind of setup for other objects as well. And so to wrap up pretty much the presentation here, I'm just going to go through some of the different images that I've made with a setup like this. And then on the left here, I put the focal length, so it just gives you an idea of what kind of lens I was using for this image. So this is from my backyard in New Hampshire. Usually when you do a star trails photo, you point at the North Star, so then you can see those nice circles. But if you point to the east or west, I think you get this other kind of interesting effect. So that's what I'm showing here. This is pointed to the west.
So the color in those tracks, is that the actual color of the celestial objects?
Yes.
It is.
Yeah, that's the color of those stars. Yeah. So the reason we don't see that color with our eyes is just because our eyes aren't very sensitive to color, but also they're just these tiny points of light in the sky. So when you make the star trails, it really makes that color of all the different stars very evident. So there's a lot of, you can see white stars, but then there's also a lot of blue stars, orange, yellow, all different colors. Okay, this is a fun event. It's usually in August, I think. This is the Perseids meteor shower. So it goes basically all night, and you can capture lots of meteors. I composited a bunch together just to show a number of the bright ones across the night. But it's also fun to view this, just to watch shooting stars. This is sort of a different kind of Milky Way picture. So often you'll see the Milky Way with a landscape, and I like taking those too, but I just wanted to sort of focus the eye on the bright red nebula in the core of the Milky Way. So like the Lagoon and Eagle Nebulae in the core. So that's why I framed it like this. This is about 500 pictures stacked together. This is the Orion constellation. So it's available to shoot right now. If like right at dark, you can go start shooting it. It's to the south. Orion the Hunter, it's a little bit hard to see in this one, but the Orion's belt is right there in the middle of the picture. And then we have Betelgeuse, the bright yellow star on the left, and Rigel is the bright blue star on the right. And you can see that Orion is full of nebulosity. It has all this bright red hydrogen, and then there's of course the famous Orion Nebula, the horse head. That little dust cloud up there in the upper right is called the witch's head. So there's a bunch of stuff to capture in Orion. My thinking is sort of the summer version of Orion is Cygnus, and then it's another constellation that's very good here for the northern hemisphere that is full of nebulae. I can name them off, but it's not particularly important, but that bright blue star in the center is called the Neb. So if you can find the big cross in the sky, you can shoot Cygnus. Okay, and then this was a recent video that I was really proud of. This is the North Star. And a lot of people don't realize that around the North Star is all of this beautiful dust. There's dust out in space. And you wouldn't think that the North Star would just be surrounded by this dust, but it is. And the cool thing about shooting the North Star is the stars don't move as fast around the North Star because everything is rotating around that point. We can actually take much longer pictures when we're shooting at the North Star. So instead of 1 second pictures, here I was taking 15-second pictures. And that makes a big difference in how dim a thing you can pick up. So this is actually a very dim object. It's called the Integrated Flux Nebulae around Polaris, but it's possible without a star tracker just due to the fact of how the Earth's rotation works. Okay, this is not a particularly beautiful picture, but it's just fun because that's called a planetary nebula. It's named that because when astronomers first saw these, they thought they might be planets, but they're actually dying stars, or stars that are dying stars is accurate. They're stars that have already outgassed a lot of their gas, and so they make this sort of bubble of gas in the night sky. So they're usually not very big. This is actually one of the bigger ones, and it's still not very big. It's called the Dumbbell Nebula in Cygnus. So it's maybe a little bit more of a challenging object to try like this without a telescope, but it's still possible. And another thing I like about it is there's not a lot of objects in the night sky that are green, but this is one of them. So if you want to find a green object, this is a cool one to shoot. And then this is another nebula that you can shoot right now. This is called the Pleiades or the Seven Sisters, and it's in the constellation Taurus, and sort of near Orion, but it's to the south and maybe now a little bit to the west, I guess. And it's very easy to find because when you're looking, you'll see this little knot of bright stars, this little cluster of bright stars, and then it's very easy to aim your camera at that. But then when you take a lot of pictures of it, you'll see that little cluster of bright stars has all of this blue reflection nebula around it. And I think that that's another really pleasing thing to bring out is a nice blue nebula. Okay, and this one I took with a really big telephoto lens, but I wanted to show it because it's coming up. There's another lunar eclipse coming up in 2 weeks that will be visible right here. It will be on March 14th, the early morning hours of March 14th. So if you either want to stay up or set an alarm and get up, it's an opportunity to see the moon turn red. And the reason this happens is because the sun is lined up where the Earth is right in between the sun and the moon, and so the moon is completely covered in the Earth's shadow. And the reason it's red is because there's still some indirect light going through our atmosphere. And our atmosphere basically disperses all the blue light, but lets the red light get through. So you're seeing sort of all the sunsets of Earth projected onto the moon, and that's why it turns this blood red like that. So it's cool just to watch it, but it's also pretty easy to photograph. You can just point your camera at the moon, take a 1 second picture, and you'll get a nice red moon like that. All right, so I left 10 minutes for questions. Thanks so much, and I'm happy to answer any questions.
So how do you re-aim when you're looking at Andromeda every 30 seconds? Because you can't see it with your naked eye.
So the question is how do you re-aim on Andromeda every 30 seconds if you can't see the galaxy in live view? What you have to use are bright stars that you can see in live view as basically signposts. Basically be like, okay, there's this little collection of stars right here in this corner. I'm going to remember that, and then when I move the camera, I'm going to put it right back in that corner. It's a good question, and that's also sometimes how you have to find these things. Is you can't find them in your camera by just trying to look for them. You have to look at the bright stars and the patterns they make, and how that will look on your camera to actually find them on the screen.
How accurate do you think these apps are, like Stargazer and things like that, in line with what you just said? If I attach my phone right to my tripod and, oh yeah, that's where it is there. I can't see it, but it just says it's there.
Yeah. So the question is, how accurate is the planetarium app on your phone for guiding you to the right spot? Pretty good. I found that Sometimes what happens though, I have my phone here. I don't know where my phone is, but my phone has like a magnet case on it, like for my car. That magnet will really throw off the internal compass on the phone. So I take that case off. The other thing to do to calibrate the compass is make a figure 8 like this with your phone. It doesn't matter even if you have an app open. That will calibrate the compass. After that, it's pretty accurate, I found. Now, is it going to put the object right in the center of your screen? Maybe not, because it's still only going to get you to the general area, but it's not going to really lead you astray. So it will get you to that general area, and then you still might have to do a little bit of trial and error to find it. I do have a video on this called How to Find Anything in the Night Sky, and I do that exact thing you mentioned of sort of putting my phone bracketed next to the camera, using that as sort of a general finder, and then use star hopping to actually make sure I'm right in the right spot.
This question is going to be a little fuzzy because it's I'm bringing back a recollection of something that I think I remember, where cameras on phones at one point, maybe they still do block infrared. Am I way off on this?
No, you're right.
So how big a problem is blocking the infrared?
We actually want to block the infrared. So the question is, do cameras block the infrared, and is that a problem? And yes, they do, and for the most part, we don't want infrared in our pictures. Because a camera can't actually focus on what's called the visible light, the light that we can see, and the infrared at the same focus point. So if you're letting in all the infrared, what you end up getting are stars that are bloated, and they sort of take over your picture a little too much. We want nice, tight, small stars. So we actually want the camera to block the infrared. Now, the problem you find is that a lot of just off-the-shelf cameras, DSLRs or whatever, block a little bit too much of the deep red light. And that's where a lot of these hydrogen emission nebulae live. They live at like 656 nanometers, which is a deep, deep red. And so sometimes the infrared cut filter on a camera will actually block most of that. And so what some people do is they remove that filter and replace it with one that lets in this but still blocks the infrared. That's called modifying your camera. And so it's a little bit more of an advanced kind of thing to do, but a lot of astrophotographers find they like to just buy a very cheap DSLR and modify it, and you get really nice results that way. When you're just starting out though, I wouldn't really focus on those red emission nebulae. I would focus on the bright nebulae of other colors, and you don't need modification to do any of those.
Thank you. Nobody else? I have one more stupid question. Why? I didn't quite grasp the understanding why you can't just focus on infinity. Why there's fine grades of infinity?
Oh, yes, it's a good question. So the question is, why can't you just set your lens at infinity and then you're done? Because from our point of view, or from the camera's point of view, all of these stars, everything out in space, whether it's planets, the moon, they're all at infinity focus. So that might be a little bit confusing, but basically what infinity focus means is everything past a certain point for that lens becomes infinity focus to it. So as long as, it could be 300 meters, and then everything past that is called infinity focus. In the film era, infinity focus was an actual hard stop, and film cameras, the lenses were made such that you could do that probably. Just set it to infinity and you'd be good for astrophotography. With modern lens design and digital cameras, infinity, when you actually look at the lens, it's like a range of values. And the reason they do that is a couple reasons. One is that digital cameras are much more sensitive, so any little bit change of temperature can actually contract or expand the glass elements in here and throw off your focus. So there can't just be one value for infinity, because at a different temperature, infinity might actually be at a slightly different focus point. The other reason they do that has to do with autofocus and how it works. If you watch autofocus, it hunts, right? So it actually wants to be able to go past infinity and then back to infinity. And so a modern autofocus system, a hard infinity stop doesn't really work as well as being able to go past it and then back. So I think those are the two main reasons why there can't just be like a hard stop for infinity that you set your camera to.
Thank you.
All right, well, thanks. I'll stick around for a little bit if you want to come up and ask individual questions. Thanks so much.